examining this item clearly, you would see that there are two specific paths here. You would see that the function is to go along a straight line from the first path, which is 0, 1 to 2, 1. Then after that, it would be from 2, 1 to 2, 5. So obviously here, we're going to use later on the additivity property for our integrals, because our given integral from p of xy dx plus q of xy dy on our given path is actually can be broken to two different paths. You have your p of your xy dx plus q of your xy dy along your first path c sub 1, plus you will have here p of the same function xy dx plus q xy dy for your second path. And we can see here that our given path, the entire path, is the union of your c sub 1 and c sub 2. And since c sub 1 and c sub 2 is connected by a certain point, we can use here additivity rule that we are going to show or solve for the first integral on the first path, then add the result for that for the integral of the second path. It would comprise for the integral of the entire function. Now, we know that still these two would be equivalent to this form when we use the parameters for x and y in using the variable t, or the parameterization of both of them. So you will have here p of your x of t, y of t, times the derivative of your x of t, plus q of your x of t, y of t, times the derivative of your y of t with respect to t from a to b. But there will be two versions. One version will be for c sub 1, another version will be for c sub 2. So we'll have two sets of a's, b's, and then x of t's, y of t's, and their corresponding derivatives. Now let's examine closely what would be the paths that we're going to solve, because there might be some possibilities that the first path is a circular path, then added with a parabolic curve or a straight line segment. Let's try to find out here. On our first path, let's say c sub 1, this one here, c sub 1, we could see that from 0, 1 to 2, 1, the value of y did not change. Only the value of x changes. If we're going to look at that in a certain plane, okay, you would see that it forms a horizontal line segment path, because the y's are actually specific or constant as x changes its value. So the first path is a horizontal line segment path. In short, for the first identification of our integral, we're going to use the parameterization for the horizontal line path. Our c sub 2, on the other hand, as observed here, x is constant and y changes from 1 to 5. This would mean that our in a certain plane, the x's are constant and the y, the vertical one, is changing from 1 to 5. Obviously, this is a vertical line segment path, and we're going to use the specific parameterization for that specific situation. Now, let's look at the process intended for this. Of course, we know that our p of xy is this one here. You will have 3x plus y, and then your q of xy is this function 2y minus x. Let's look into that separately later. Okay, so first let me divide this one here, and of course I'm gonna ask your consideration, as I will be adding a separate page later on, and this video would take a long time as we are going to discuss both of the paths separately before combining them. This would be for the horizontal line segment path and the vertical line segment path. For x of t needed for our integral here, that means we're going to parameterize x and y for our function p and q for this specific path. Take note that in our situation earlier, it's called horizontal line segment path because the x changes the value and the y are constant. When y is constant, you can assign it to c, or the value that did not change, which is 1. So that means our y here is 1. But for our x, since it's the value that changes it's the item that changes its value from 0 to 2, we can assign it with t. Connecting to that, since our t is the between a and b, and t changes from 0 to 2, that would mean our a is 0 and b is 2. So a is 0, b is 2. For the vertical line segment, we can see here that the x did not change, or x being constant, and the y changes from 1 to 5. So obviously you can compare it here. Our x of t for our second path is the one that did not change, which is equal to 2, and our y of t changes from 1 to 5. That would be your t. Again, your t would tell us your a and b. T changes as assigned to y, changes from 1 to 5. So you have your 1 to 5. Our a is 1, our b is 5. Okay? As you can see here, for horizontal line segment, it's x of t, which is t. But for vertical line segment, it is your y, which is t. Now, with this idea, we can now continue identifying, okay, the first derivatives of your x and y needed for both situations. So here, your first derivative for t is 1 with respect to t, and your y derivative of 1 is 0. For the other side, the derivative of your x of t being x of t is 2 is 0, and the derivative of your y of t is 1. Okay. Now, aside from these ideas, we already have the first derivative of x and y. We already have our a and b for both paths. What we need to do here is the functions of p and q using the correct parameters for both paths. So we're going to assign here the correct functions before we can use the integral. Take note that originally our p of xy is identified as 3x plus y. 3x plus y. So if you would like to have x of t and y of t, changing the functions, the variables, instead of 3x, you'll have here 3 of x of t plus y of t instead of y. This is true for both situations here. The only difference is that your x of t and y of t differs from one another. For our horizontal, the first path, your x of t is t. This is a 3t plus your y of t is 1. Okay? For our vertical line segment path, similar thing. Your p of x of t here, y of t, would be 3 times your x of t, which is 2, plus your y of t, which is t. So this is actually equal to 6 plus t. Okay? That is actually the idea for the parameters. That would describe your function p. Okay? Now, for our q of xy, which was originally 2y minus x. 2y minus x. If you would like here q of your x of t and y of t, you will have here 2 of your y of t minus your x of t. Again, for both of them, they will just differ on the correct forms, because for the first path, your y of t is 1. So you have here 2 times 1 minus your x of t, which is t, which would give us 2 minus t. As for your second path, your q of your x of t, y of t is 2y minus x, right? So your y is t. So you have 2 times t minus your x, which is 2. This is equivalent to 2t minus 2. Alright, now we all have the details now needed for this specific formula. So what we need to do here is to simply use them in our formula. So allow me to add other page here, but first let me copy and add another page. I'll be placing them here. So this might actually limit the spaces here for this next page, but this is very important so that we will not be returning from one page to the other, okay, as we move for look for some details needed. So I still have here the Q. I need to copy the Q here. All right, so copy, and again this page here, hopefully I can overlap them correctly. All right, so you have this. Okay, so we now have these two forms, so we're going to solve for each of them separately. For the first path is the horizontal line segment path, and we have here the vertical line segment path for the second path, or here C sub 2. Okay, so let's start with the first one, the horizontal line segment path. So what we need here is the application of this formula entirely. So going back here, so this is integral of your a to b, which is 0 to 2 of your, look at the formula here, p of x of t times the first derivative of t. So your p is actually this one here, 3t plus 1 times the derivative of your x, which is 1, plus your q, 2 minus t, times the derivative of your y, 0 dt. Okay, if we're going to duplicate that here on the second one, so you'll be able to compare them. Your a and b is 1 to 5, so 1 to 5. Your p was 6 plus t here, times the derivative of your x, which is 0, plus your q, 2t minus 2, times the derivative of your y, which is 1 dt. Okay, so let's attack them separately. Let's have the horizontal first. So you're going to simplify the content in the here. So this is 0. So of course that's times 1. It would still be 3t plus 1 with respect to t. So applying the linearity property, you will have your 3 times the integral from 0 to 3. Ay, sorry, it's not 3, my bad. My answer would be different later on. So 0 to 2 of your t dt plus the integral from 0 to 2 of dt. Okay? Take note that the integral of your t dt is t squared over 2, and the integral of dt is just t itself. So you will have here 3 times t squared over 2 from 0 to 2 plus t, okay, the integral of dt, right, from 0 to 2. So with this now, substituting the boundaries, you have 3 times 2 squared over 2 minus 3 times 0 squared over 2 plus 2 minus 0. We know that 2 squared over 2, or let's say 2 squared is 4, divided by 2 is 2, so 3 times 2 is 6. This is actually 0, that's also 0. So you have 6 plus 2, which gives us 8. But this 8 is just for the first path, this one here. Just a portion of what you're trying to solve, since it shows a piecewise path. Okay, it's a piecewise path. Okay, now for the second, which we need, of course, is to continue this one here. So you are going to multiply whatever items you have inside. Basically, that's also 0. You will have here 2t minus 2 times 1. So we have dt. Using the linearity property, 1 to 5, or let me use the linearity property here, you will have 2 times the integral from 1 to 5 of your t dt minus the integral from 1 to 5 of your 2, sorry. By the way, you have 2 here dt because we have 2 constant here. So you will have here again the integral of t dt is t squared. So you have 2 times t squared over 2 from 1 to 5 minus 2, and integral of dt is just t from 1 to 5. Now, one thing you need to notice here is that the second term is preceded by a negative sign. Make sure that once you substitute these boundaries, make grouping symbols or add grouping symbols so that you will not be confused with the correct difference later on. So I could also try to simplify that easily. So what we have here is 5 squared minus 1 squared. Then minus, again, the grouping symbol, 2 times 5 Okay, minus 2 times 1. We are using the grouping symbol because our second process is negative. So hence, you'll be using double negative property. If you're not going to use the grouping symbol there, definitely you will have an incorrect answer. So let's just finish this one here. 25 minus 1 minus 10, double negative property plus 2. So this is actually 27 minus 11 is actually 16. Right? So that is, of course, again, just the integral of your second path for your vertical line segment path. This movement here. Okay? So, since, again, the two paths are connected at 2, 1, we can use here the additivity property or the concatenation of points for the integrals. And obviously, we just need to combine them. So our final answer here is 8 plus 16, which gives us 24. This is now the final answer. This is the combination of the two paths, and this is now the real line integral of the given function here along straight lines, combining the horizontal line segment path from 0, 1 to 2, 1 and the vertical line segment path from 2, 1 to 2, 5. Combining all of these details and separate forms of x of t's and y of t's, your parameterization, connected to the considered path themselves and their corresponding boundaries as well. Thank you very much for watching.